Welcome to Through the Lens, a series dedicated to reveal the people behind today's breakthrough in optics. For the first season, I'll be sitting down with fellow members of the optics department of FEMTO-ST Institute in Besançon. We'll talk about their research, what motivates them, and their personal journeys. Come along as we explore the human story driving photonics forward. So today on the podcast, we are interviewing François Courvoisier. He's the director of the optics department in FEMTO-ST in Besançon. Welcome, François.
Thank you.
Can we start the interview with your introduction? Tell me more how you ended up in Besançon professionally.
In short story, I'm originally from Besançon, but I didn't do any of my studies here. So I went to École Normale Supérieure of Cachan, just near Paris, and then for my bachelor and master, and then I moved to Lyon for my PhD, and I have met my PhD advisor while I was in internship in Yale University, and then I moved to Geneva for a postdoc, and then finally landed up in Besançon on a completely new theme, but that's how life happens.
Okay. And the topic of your PhD was ultrafast laser physics, spoken generally. Can you tell me, how did you choose this topic after your studies?
I was attracted by applied physics. So I wanted that, for sure I wanted to be a researcher, that was clear. And I loved the idea of having a field of science that was also with some purpose behind, with already an idea of what will it be useful for. And so the idea of my PhD was about typically detecting bacteria from the aerosols to know if they are dangerous pathogens or not at all. So it was ultrafast spectroscopy.
Okay, yes. And then during your postdoc in Geneva, you had the same topic?
It was a little shifted. It was still biophotonics more at the time. We wanted to pursue two directions. The first was to develop nanoprobes that were able to get a track of the environment, of the molecular environment, using a nanocrystal that could be a source of light, but extremely localized. And the other part was a little bit more linked to my PhD because it was still ultrafast spectroscopy, but there we wanted to really identify the molecule by shaping the pulse in the time, and being able to see how the molecule would respond, and be able to discriminate molecule per molecule if one is very dangerous or if it is its close neighbor. But we wanted to have a better degree of control, or a better measurement. Using it was based on genetic algorithms to discriminate molecules that were extremely similar.
Okay, and so the molecule that you can detect depends on your laser light, right?
Yes, yes.
Yeah,
it was.
So what kind of molecule were you able to work with?
Well, we made a proof of principle to discriminate, if I recall well, it's some time ago already. We were distinguishing flavin mononucleotide compared to riboflavin. And in fact, the two have exactly the same spectrum, but when you excite them with different, when you excite with the first pulse and you shape a second pulse, then you with the shape of the second pulse, you can enhance the fluorescence of one of the two molecules compared to the other. And with this, you could expect to discriminate them better. And that was opening a route toward molecular identification of some pathogens. But in practice, this is a nice idea, but now that AI has a lot improved and evolutionary algorithms are better, now it becomes more feasible to make this to really detect a bacteria compared to another one. But at the time it was still very preliminary ideas.
Okay.
But that worked well, yes.
And where can we find those molecules?
Those molecules are from, these are inside the cells. So these are, riboflavin is vitamin B2.
Okay. Okay, I see. And then you mentioned just in the beginning that from your postdoc to after your postdoc, you changed completely the topic. What was the turning point between Geneva and Besançon? The turning point is, okay, I established a new career as CNRS researcher, and then I had to propose a project. And here the topic around was not at the time really around biology, but there was lots of activities around micro nano fabrication, and I had made some experiments during my PhD around filamentation of high power femtosecond laser pulses, and I decided to reuse that and this knowledge, but at micro nanoscale. And the initial idea was, okay, how can we get a kind of beam with filamentation that could help us in processing materials? And this made an initial track that we continued, and in fact it worked very well for glass dicing at super high speed, for instance. Okay, and I'm guessing the physics is quite different from the different scale that you studied, no? Or
yes, the physics is very different from from ultrafast spectroscopy, except one thing, the tool, which is a femtosecond laser. So high power femtosecond laser, I was used to use them, and then this was something pretty easy for the transition, but that was the only thing in common.
Yeah.
So I had to learn again a completely new field.
Yes. Every time we change the scale in physics, I have the feeling it's an entire different world.
It is.
Yeah. Okay, so until a few years ago, 2024, you were a scientist, and now you are director of the department. I want to know how your work changed, and how do you deal between the creativity and the administration task?
That's a nice question. In fact, in France, being director of a department or being director of a lab is pretty much a task that it's a time you dedicate to your colleagues, and the idea is to help the department evolve smoothly. And the thing is, yet it's a lot of administrative tasks, so we try to simplify things and simplify the procedure as much as we can, but it's not always feasible. But what it's nice to see is it opens up some opportunities to discuss a bit some fields with colleagues and see how I could help a bit, or just make the nice suggestion or the nice contact with some others, and when it matches, I'm happy. So this is a nice thing to do. Yes. Okay.
So you still have a large part of creation in your work currently.
Yes. Creativity is still there, and this is I still have some time for my research, and I still have, there is a little part that I enjoy a lot of creativity for the optics department, which I try to amplify, but in the margin I have, I'm pretty happy with that, yes.
Okay, nice. Okay, let's dive into the science topic. So when I look at your profile, I found three main topics. First, Bessel beam, so more about beam shaping, and then I saw that you had a big project called the Pulsar project that is about ultrafast laser ablation, and the last one that I'm particularly fond of is the nanopillars. Mm-hmm. First of all, we're going to start with the Pulsar project. If I understood correctly, it aims at controlling plasmas inside materials. Can you explain what is a plasma for the students that are listening, and why is it so important to control them?
In laser matter interaction, when in ultrafast laser matter interaction, so ultrafast means that we have a flash of light that is about 100 femtosecond in duration, so this is 10 to minus 13. So this is extremely high electric field during a very short time. And during this irradiation time, the electrons of the material, for instance, if we are looking at a dielectric like glass, electrons are ionized, or say the atoms are ionized, or in semiconductor you would say electrons are promoted from the valence band to the conduction band. So we promote lots of electrons to the conduction band. Sometimes we also excite them extremely far in the conduction band, and at the end of the pulse we have what we call a plasma that is composed of highly excited electrons and holes, or highly excited electrons and ions, but all this is globally a plasma within the material or within the dielectric. And the thing is that the plasma is extremely important because its presence changes completely the permittivity or the refractive index. So it changes completely the way the pulse will propagate into the material. And because of that coupling, it's crucial to know and control the growth of the plasma, because it will completely modify how the pulse will deposit energy inside the material. And if we change the way we deposit energy, we change the way it is ablating, for instance, or the thermodynamics that will happen after the pulse.
Yes. So tell me if I'm wrong. It seems that the plasma is acting a little bit like a mirror and rejecting the laser energy. How do you avoid this?
In fact, we try to circumvent or we bypass. This is a way where we made a new approach, is that in fact if you use the right beam shape, in fact you can create a plasma, you can deposit energy via this plasma inside glass, for instance, and the pulse goes from the sides. And this is exactly the shape of the Bessel beam that you were mentioning before.
Okay, yes. So the main idea in this project is to reshape the light to reshape the plasma.
Exactly. So the project the idea was to control not only the shape of the pulse, but the shape in space and time, to control the density of the plasma and to be able and create extremely strong micro explosions inside the material. So extremely reach high energy density inside.
And can you think, or do you know any current industrial application that could use this process?
In fact, they are using already. We have developed, for instance, the Bessel beam shape applied to nano drilling. It was in 2010, so some years ago, and quickly people have seen that this could help to cut glass. And because you can make one nanochannel and another and another and another, and this induces a plane that is fragile inside glass. And if you apply a stress, then glass is cut very high, very quickly. So many industries have used this process to cut glass at 1 meter per second, and this is the one that is typically used now to cut, for instance, the front screen of your tablet or your smartphone.
Mm-hmm. Okay. Yeah. Very
so
nice.
it's already used. Yes.
Yes. We're going to talk about the Bessel beams that we both mentioned. I've seen that you're going to soon present some work in SPA Strasbourg, where you have this millimeter-long nanowires that are created by single shot, and you're using higher order Bessel beam. So the first question is, can you describe what is a Bessel beam and how does it differ from Gaussian ones?
A Bessel beam is very simply it's an interference. So if you have two waves that cross, you will have the conventional two-wave interference. But if you add a rotational symmetry, then you create what we call, in fact, a Bessel beam, which is a central spot surrounded by several lobes of lower intensity. And the thing is that this shape does not, because it's an interference, the shape of the hotspot doesn't change with propagation distance, contrary to Gaussian beams, which evolve to diffraction very quickly. And if you want to have a sub-micron spot using a Gaussian beam, then it will exist only over a distance of 2 microns, whereas with Bessel beam, you can create a sub-diffraction spot, typically close to lambda over 2, over 1 centimeter.
So you can use the property of the focus over a very long
distance.
It's
a very long focus, yes.
And one thing that is quite interesting also with the Bessel, but I don't know if you're using that as well, is the self-healing property of the Bessel beam. Is it any relevant?
Yes, it is very relevant. Thank you. Because in fact, one part of the Bessel beam creates a plasma, and because the plasma is highly absorptive and also reflective, in fact, because of the shape of the Bessel beam, the Bessel beam can come after from the sides and avoid that part of the beam that was somehow blocked, and it can create again the plasma further and further and further, so that we have, after the pulse has passed, a continuous line that is completely homogeneous, where we have extremely high intensity, high energy deposited, and which is creating these micro explosions to open voids.
Yeah, so that I found particularly fascinating, just that you obstruct the light and it still doesn't.
Yes, but it's not a big trick. In fact, it's just coming from the sides.
Yes.
Because of the interference property.
Yeah. The aspect ratio between channel length and diameter that you achieve for these particular channels are quite extraordinary. It's 200 nanometer in diameter, which is like 500 times smaller than a hair, and a few millimeter long. Mm-hmm. What physical mechanism allow such an ultra long nanochannel to appear?
In fact, this is precisely the homogeneous energy deposition due to the Bessel beam, for instance, that can be formed on nearly sub-wavelengths over whatever distance we can, and we have kind of parallel explosion that exists either as a line or as a cylinder, as you were mentioning, for the higher order Bessel beams.
Okay. And what is still there to improve for your industrial application?
For applications, what remains to be improved is first the understanding, because we are operating at sub-diffraction level, so it's extremely hard to get information on the plasma properties themselves. So how the process works actually is still half an enigma in some materials, and in others completely. So for instance, in semiconductors, this is still really challenging to make the same process, and we need to understand the why and how to circumvent that, because we need to develop things to overcome this. And recently, yes, we developed some new shapes that can be formed after the interaction. For instance, using other beam shapes, yes, like higher order Bessel beams, or playing with the polarization, playing with a special temporal shape. It opens new perspectives too, and so lots remains to be seen. How can we engineer or control the material modification, and upon the control of the laser pulse? And I think you can change materials, pulse shape, etc. And then each time we can go into a new field or discover new potential applications.
Mm-hmm. Okay. In your recent work on nonlinear printing of platinum, you use a technique called two-photon induced photolysis. This is a particular question for this, but actually I think it applies to all your work. Can you explain the principle of this technique? And then what is the advantage of nonlinear absorption at nanoscale?
Yes, thank you. So for the non-linearity is very important in my work, or in our work in fact, because if a process is nonlinear, this means that it is more likely to a process will be more likely to happen in the region of a beam where the intensity is higher, and the contrast is improving with the order of the nonlinearity. For instance, if we want to create an electron-hole pair in glass, the transition is about 6 photons. So it is intensity to the power 6. So if you have a simple Gaussian beam, if you put the intensity to the power 6, the region where it exceeds this threshold will be a very tiny sphere that is at the focal point. And then this means that I can deposit energy on a nanoscale in 3 dimensions inside glass without touching anything on the side, on the surface, or it can be even in presence of something else. And we have a completely new degree of accessing or depositing energy inside something very hard to access usually. And this is how we can process materials, that transparent materials, because it needs to be transparent to the laser light. But we can also make, like in this with this 2-photon photolysis, we can generate new materials from a liquid solution. And that's a nice idea, and then this opens up many things on 3D printing, or this kind of field where all 3 dimensions are important.
Yeah, it seems to work just like a tip. You're using only the tip of your pen. If we can say that the light is a shape of the pen.
Yes.
For Gaussian beams, then you use only the pen, and it makes it very precise. And that's the advantage now of this.
Yes, this is extremely precise, because we can affect materials on scales that are typically, it can be below 50 nanometers. So, and this is in 3D. And all lithography techniques are usually only in 2D, or we can say 2.5D. It is difficult to drill through, but you can never make something completely inside. And here with lasers, ultrafast lasers, we can write things completely inside materials.
Yeah. And how do you control what you draw? I'm thinking it's probably the light, but what parameters of the light can you tune to have a better control?
This is an interesting question. Yeah, there are 2 points. How do we characterize? We have, for now, because we are writing things inside materials, or it's mostly only optical probing. And how to control the laser pulse? Usually we use beam shapers, or based on spatial light modulators, or we can also use diffractive optical elements, or completely surfaces that are deformed. For instance, to generate Bessel beams, we can use axicons that are using a conical mirror.
Yeah. Okay. Thanks. The last part of the interview are general questions that are not all linked together, but there are some of the topic I would like to address with you. So, in your opinion, what is the most important skill a PhD student should develop today?
Today. Today and in the past, the first is, I would say, resilience. Because the first thing in science, a PhD student will hit always a wall. Because if the science he or she wants to develop is new, it has not been before, and if it hasn't been done before, it's because it was difficult, or it has to be generated from new ideas. So very likely it won't work the first time. But it won't work the second time, and it probably won't work the third time. And then you need to be resilient enough to push a fourth and a fifth time and maybe a 10th time, and then it works. And then you grab the good parameters to get your ID work and to be in the right conditions. So resilience is the first quality to develop, because yes, it will be very important. As a second one, I would suggest something like network. Networking is an important, and I think you can also enjoy that.
So on a global scale, only 1/3 of scientists are women, and from a recent evaluation from Eurostat, France is doing worse than countries like Spain or Poland. What concrete actions can research institutions can do to fill this gender gap?
Have to face the gender bias, which I have observed. That's very clear. We have to overcome that, and typically this is so we can claim for equality. At least this is a minimum that we can do. We need to push, I believe, to have good standards. But what works most, in fact, is, and this is extremely hard to do, is when there are sufficient amount or sufficient percentage of women in a group, then automatically, then this number grows. So we have to reach a critical mass where, in fact, women feel comfortable or anticipate that the group will be welcoming enough for them, and that's the way we can do. But this is not at the institutional level. This is at the group size. And this is maybe for institutions the most difficult part, how to push individual groups to hire more, and sometimes it just happens on opportunities to get, okay, can you have the opportunity to have enough women candidates to fit the position? And sometimes in some fields, even mine, it's extremely hard. But I had one wonderful female PhD student. I was very, very happy, and I wish we can have more.
Yeah, and what I like about the FEMTO-ST Institute is that a lot of researchers here make a point about presenting what they do in high school or even before that. And so I think there we have a critical advantage to recruit even before PhD, where you can start a passion for science with the right ingredients. Yeah.
Yes, I think it's important, yes.
Yeah. François, many thanks for this very interesting interview.
Thank you for the invitation.
Yeah, it was a pleasure to receive you, and that's all for us. Thank you.
Thank you.